Hello, everybody. I wanted to talk about this covalent and ionic compound app that we're probably not going to be able to use in class much. So if you will go to the PowerPoint that I'm going to post, the link to the app is right here, but you got to probably download the Java file to be able to run it. So I'll just show you some of the things here in class. So here's the app. And we're going to start with taking a look at these ionic and covalent compounds in a solution. So let's start with sugar, also known as sucrose. And here I'm just going to dump all these sugar molecules into this water. This is pure water. And you can look and see here that the sugar molecules stay together and they're just kind of floating around doing their own little thing. So if I get rid of the sugar, let's use salt instead, which is sodium chloride. Here's our sodium chloride, just dumped it all in. And look at these molecules. Or look at this salt, I should say. Look at that. The water has somehow interfered with the ionic bond of the sodium and chloride. So yes, ionic bond is stronger, but one of the properties of ionic bonds is that sometimes it can be readily dissolved in water. And let's take a better look why. These are examples of water molecules. The big red ball is an oxygen atom. The two white ones are the hydrogen atoms. We're going to talk about these plus and minus signs real quick on here, but they kind of represent that there's like a slight charge on the positive charge on the hydrogen and a negative charge on the oxygen, similar to what the ions have for the negative charge on chlorine and positive charge on the sodium. Now I'll take let me take my salt crystal and dump it in my water, and it's all happy bouncing around. And as discussed in the last app that we just saw, it's separated it real quick. Let me pause it. Take a look at this one right here in this left-hand one. Notice how it looks like almost all of the oxygen surrounding the sodium atom has the oxygen trying to touch the sodium atom. And notice negative charge on the oxygen, positive charge on the sodium. This is what's keeping the sodium and the chlorine from joining back together again, because oxygen is trying to butt its way in there. Oxygen is a very, very greedy element. It's trying to butt its way in there. And we're going to talk more about this in hydrogen bonding and other forces in a few weeks. But let's talk about conductivity. So we've seen how a ionic bond will break apart in water. We've seen upon how the water keeps it from rebonding together and how it likes to move around. Now let's see what happens when I put a battery on it or see what its charge is. So here's a little gizmo you can make at home. I tried it myself and I got a little reaction, but it's easier to see with this app. And I'm going to take this setup with a light bulb, a battery, and two electrical leads in pure water. Let me dump some sugar in there. Dump my sugar. Here's my sucrose. Dumping, 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 dumping. And absolutely nothing happens, but you're getting sugar on these wires. All right, let me get rid of the sugar. Let's add some salt. Watch the light bulb. And this really happens. As I'm dumping the salt, the light bulb is slowly turning on. So here's a good chance to pause and think why this is happening. Okay, now that we had a chance to talk about that, let's discuss more about why this is happening. We already said that the sodium and the chlorine ions are going to disassociate because the water is just getting in the way and the oxygen is preventing the sodium from rejoining with the chlorine. That's causing these positive and negative charged molecules to run all through this water solution, which is allowing electrons to move all through this water solution. And because the electrons are moving, it's actually causing the charge to move and turn the light bulb on. This is why pure water cannot conduct anything. Salt water is highly conductive. So, food for thought.